9.3 looks at the central limit theorem. This is kind of the start of where we're going for the rest of the semester with this stuff. It's not a particularly easy chapter, so bear with me on this. There is a lot of information that I have to give you, but at the end, the examples that you use are kind of repetitive, so once you get the hang of them, they're not too bad. But I'll give you some background first so that you can see where this thing kind of comes from. We won't go through all of it, but at least you'll have some more intuition about what's happening. So what the central limit theorem does, instead of just looking at a specific point to estimate, let's say we're taking our mean, is going to kind of give us an idea about what is happening for this sample or for our population, okay? So we use these summary statistics like our mean, our variance, our standard deviation. We're using a single value to kind of tell you something about that sample or the population. What we are doing this time is we are looking at what happens when we have our population mean. We're going to have we can take samples from our populations, and each one of those samples in the population is going to have its own sample mean. Now, as long as we've got representative samples throughout, those sample means should tell us something about the population mean. They should be fairly close to it. You should be able to estimate the population mean using the sample means. But what else can we find out about our sample means and what actually happens within all of this? That's what we're going to be looking at today. And it sounds like a weird concept, but bear with me and you'll see how it works at the end with some of these examples. So first of all, what I want to look at is looking at these sample means. So I'm going to draw a quick number line. Okay. And let's say you're going to have data points all along this line. So all along this line, you're going to have these points that are all data points within your population. Okay, so all along that line, you have data points within your population. Okay, and somewhere in that, you're going to take a mean of those data points, and that is going to be your population mean. So mu is your population mean. So all along there, you have all of your data points, and you've taken a mean of those data points, and you've denoted that on your number line. So you have your population mean. Now what I'm going to do is I'm going to say, okay, let's take a representative sample of all of these data points. So you've got all of your population data points, but I'm now going to take a sample of them. Let's say here, here. Okay, let's take, I don't know, 5 of them. Okay. So I've taken 5 data points here, and that is a sample of my whole population. Now what I'm going to do is I'm going to take the mean of that sample. So the mean of that sample, let's say it lands somewhere around, I don't know, here. And we'll call that X bar. So that X bar is our mean of that sample of 5 data points, let's say. Now I'm going to take another representative sample. So let's take some of these data points here, here, and okay, we'll take another 5 of them, okay? And I'm going to take the mean of those data points. Let's say that lands here. So we've got another sample mean. So you can take as many samples as you want, and each one of these samples is going to have its own mean. So you just take the mean of, in this case, these 5 data points each time, and you see where the sample mean lies. You'll see that those sample means are pretty close to the population mean as long as you have taken a representative sample. If you took all of your data points to be, I don't know, somewhere up here, so you just took all of your data points from this area, your sample mean would land somewhere up here. That is not a good representation of the mean whatsoever because you have taken all of the points that land in one specific area. So you could not estimate your population mean using the mean of that sample, okay, because it is not representative whatsoever. They all come from one area. So we have to take this representative sample where you've taken points from all across that board, all across the population, and then taken that mean. So each one of these samples is going to have its own mean. It is unbiased because we have taken a representative sample. So for each one of these samples, for each of our samples, because they are representative of the whole population, the sample means are unbiased. Okay, so that is a big thing, that they are unbiased. What you will also see, okay, is how much these means vary from the population mean. Okay, look at this spread of data points that we have within our population. Okay, you've got points all across the board. But what you will notice is that if I take the mean of each of these samples, so I have taken some of my data points, okay, and I've put them into a sample. Some of them are way out on the two opposite ends. So I've got some data points way out here and way out here. But you will see that even when those points are within my sample, I've then taken a sample mean, and my sample means land way closer to the population mean than some of the data points that are way out on the opposite ends. So what you actually see is that your sample means land close to your population mean as long as you have a representative sample, which should mean that they shouldn't vary a lot, okay? So in order to be a good estimator, a good sample mean that we can use to estimate our population mean, you should notice that they should land somewhat close to the mean, okay? So we don't have a huge amount of variation between our sample means and our population mean, okay? But if we had taken an unrepresentative sample where we took the points way up here, okay, when we took the points that were not representative, okay, and I were to take this mean up here, that X bar, that sample mean would vary a lot from the population mean, okay? It's really far away. So because in that case we wouldn't have had a representative sample, we would have had a huge variance between our sample means and our population mean, okay? So in order for this thing to kind of be a good quality sample mean, you have to make sure that you have a representative sample. That's kind of the gist of all of this, okay? Now, what we want to see is exactly how much do these sample means vary from our population mean, okay? How close can we get, okay? When we take representative samples, how much do these sample means vary from our population mean? When we say the word vary, the first thing that should come to your mind is variance. So what you actually have is that for any population that you have, if you want to see what the variance of the sample means is, so you're looking at how much these sample means vary from the population mean, you take the variance of the sample means, and that is how it's denoted. So it's sigma squared but with X bar, because you are not looking at the variance of the data points in comparison to the population mean. You are looking at the variance of the sample means in comparison to that population mean. So you are just looking at, if I took all of the samples that I could possibly take and I looked at their sample means, okay, so I'm looking at the means of each one of these samples where I have taken representative samples each time, and I am looking at the variance of those sample means in comparison to the population mean, you should have that the variance of the sample means is actually the variance of the data points divided by the number of points in each of the samples. Okay, so in our case up here, I took 5 points in each of my samples. Okay, so my variance of my sample means is just the variance of the data points divided by the number of data points in each of the samples that I took. Okay, again, don't worry about where this actually comes from. We'll look at it a bit more intuitively in a second, but just be aware that that is how you figure out the variance of the sample means. Now, when we have variance, we can get the standard deviation. So the standard deviation of the sample means is just the square root of the variance of the sample mean. So it's the square root of this fraction here. So it would just be sigma over the square root of n. So it's the standard deviation of the data points divided by the square root of the sample size in each case. Okay. Now, as I've said before, you should notice that the sample means land closer to the population mean than the majority of my data points do. Okay? Now, if you have data points that are way out on either end, as we were looking at up here, where I have data points all the way over here and all the way over here. When I have data points that are really far out, compared to where my population mean lands, that must mean that my variance is large, okay? Because my data points, I've got some that are very close to the population mean and some that are very far away. So that means that my variance would be a fairly large number. But when we look at taking samples, and then I look at where my sample means land in comparison to the population mean, you notice that my sample means land way closer to this population mean than my data points on either end. Okay, these 2 points here and here land way closer to our population mean than the points on either end. So that must mean that my variance of my sample means in comparison to the population mean, as opposed to my variance of my data points in comparison to my population mean, it should be smaller because those sample means land closer to that population mean than some of my data points do. So what we should be doing when we get our variance of our sample means, you should be reducing that value that is the value of our variance of our data points. So it should be smaller than what the variance of my data points was because they land closer. That makes sense with what we have here, okay, with our fractions. You are taking the variance of the data points and you are dividing it by some number that is greater than 1, okay, because you're going to have at least 1 point in each sample. So because you are dividing it by a whole number greater than 1, it must mean that you are reducing the value of the variance. So what you get for your variance of your sample means should be smaller than what the variance of the data points was, because you are dividing it by a number that is greater than 1. Okay. As I said, don't really worry about where that value comes from. There's more behind that, but intuitively it makes sense that you should be reducing the number, the value of the variance, okay? That you should end up with a smaller number than what you started with. Okay. Now what I want to look at is where those sample means actually lie compared to where my population mean is. Okay. What you actually find, let's go back to our diagram here, okay. If your population mean is in the middle, so your population mean is here, okay, and you took representative samples, okay, so you're taking, let's say, a sample of 5 each time, but those data points land across the board. Your sample means, so the mean of each of those samples should land somewhere around that population mean, okay? But you should find that some of the sample means will be below the population mean like we had here, and some of them should land above the population mean like we had here. So what you should actually end up with is that 50% of your sample means will actually land below the population mean, and 50% will land above the population mean, okay? This should remind you of our normal distribution, okay? So remember back to our bell-shaped curve. Okay. Our mean always landed in the middle, okay? Now, I am looking at the data points as though they were my sample means, So my data points are now my sample means. I'm forgetting about the other data points that were in my population. I'm just looking at the sample means. I should find that some of my sample means land this side and some of them land this side. Okay? And I should find that the majority of my sample means are mostly very, very close to this population mean. So I should have the majority of them, hence the height of this curve. The most frequent ones that I have should land close to my population mean. I may have a few sample means that land somewhere out here, hence why you've got a lower curve over here and over here. But the majority of my sample mean should land very close to my population mean, hence they are more frequent. So you actually end up, as long as your sample sizes are large enough, you should end up with this bell-shaped curve. This is an example of our bell-shaped curve, okay? So you can see here they've just taken something with a mean that's around 43,000 and they've got a large standard deviation as well. But when we are just looking at where the sample means lie, okay? So we've got our population mean lands right in the middle. And then we have a certain amount of our sample means that land either side, okay? The larger that my sample is, the more of my sample means I have lie very, very close to that mean, okay? And the smaller my sample size, I have more and more of my sample means actually land further away, hence a flattened curve. But the greater the amount of things that I take in my sample, so in this case they had n is equal to 200, I've got more things in my sample and I actually end up with more of my sample means land much closer to the mean, okay? So this is just an example where you see this picture here that you can actually see the larger the sample you take, the more of the sample means actually land closer to that population mean. And you end up with this normal distribution of your sample means. Okay. So this takes us to the central limit theorem. And what the central limit theorem says is that for a sufficiently large sample, so for a large enough sample, and we actually say that the sample size has to be at least 30. So you've got to have a sample of greater than 30. And you're drawing from a population where you have a mean, we'll call it mu, and a standard deviation sigma. So whatever your values of your mean and your standard deviation for your population are. The sample means will have approximately a normal distribution. So you should end up with, regardless of the size of your sample, as long as it's at least 30, you should end up with your sample means actually forming a normal distribution around your population mean. And there's a couple of characteristics that we've actually talked about, but we'll specifically state them here. If I take the mean of my sample means, now I said before, you should have 50% of your sample means are below that population mean and 50% above. But they will form that normal distribution around your population mean. So the mean of the sample means is just the population mean. And the standard deviation of the sample means is just the standard deviation of the data points divided by the square root of the sample size that I am taking each time I take a sample and take the mean of it. Okay, so your sample means have a normal distribution where the mean of the sample means is just the population mean, and the standard deviation of the sample means is given by the standard deviation of the data points divided by the square root of the size of the sample. So what we actually use this for is going back to what we've done before with Z transformations. So we're going to be calculating probabilities, and the probability that a sample mean for any sample that you take will be greater than, less than, or between some values. Okay, and we'll see this in some examples. But in order to calculate this, you have to do a Z transformation. Now remember, before when we did Z transformations, what you were doing is you were taking some data points and you were saying, okay, they follow a normal distribution, but they have some mean and some standard deviation. You weren't in standard normal, so they had a mean that wasn't 0 and a standard deviation that wasn't 1. So we used this Z transformation, and what this did was it pulled all of the data points back by the mean. So it brought it back to a mean of 0, and by dividing by the standard deviation, you give it a standard deviation of 1. So what this Z transformation did was it took it from any normal distribution with some random mean and standard deviation, and it brought it back to the standard normal distribution with a mean of 0, standard deviation of 1. So it was way easier to calculate stuff. We're going to do the same with the sample means, okay? Because remember, the sample means they have some random mean, whatever the population mean is, and they've got some random standard deviation that was given by that fraction. So they do not have a mean of 0 and a standard deviation of 1. So what I'm going to do with a Z transformation for the sample means, okay, I'm going to follow the same theory as before. So I'm going to say, okay, Z is equal to, now my data points this time are my sample means. Okay, I'm not looking at the individual data points, I am looking at the means of the samples are now my data points. I'm subtracting their mean, okay, exactly as I did up here with this Z transformation. Okay, you took the data points and subtracted the mean of those data points. So now my data points are the sample means, and I'm subtracting the mean of the sample means, and I divide by the standard deviation of those data points, or the standard deviation of my sample means. If we substitute in what we found, this is just the sample means minus the mean of the sample means is just my population mean. The standard deviation of my sample means was the standard deviation of the data points divided by the square root of the sample size. So whenever you are calculating probabilities with sample means, you always use this Z transformation here, okay? We're going to do a couple of examples so that you can see how this works. Also, just a heads up, if you ever see the word standard error, I wanted to make a point of this because I think it comes up in the learn section and you may occasionally see it in a question. If you ever see the word standard error, all that is the standard deviation of the sample means. So if you ever see the word standard error, they are just looking for the standard deviation of the sample means. Okay, so just be aware of that just in case you ever see it. Okay. Okay, so let's go ahead and do this example. I've got one example here and then I've got a couple from the homeworks that I'll go through. One of them in particular is slightly different, but you do see it come up quite a bit. So first of all, okay, this is in my notes on the Google Drive if you want to go ahead and look at this question, but I'll just write out the main points here. Our example says, a company fills bags with fertilizer for retail sale. The weights of the bags are normally distributed and have a mean weight of 15 pounds and a standard deviation of 1.7 pounds. So for our whole population, okay, my population mean is 15 pounds. Okay, and my standard deviation for those bags of fertilizer is 1.7 pounds. So I have a population mean and a population standard deviation. So these are for my whole population of data points. The question is, what is the probability that a randomly selected bag of fertilizer weighs between 14 and 16 pounds? Now, we are looking at the bags themselves. We are not looking at taking a sample of them or anything. This first part of the question, if you look at the notes, this is just referring to what we have done before, where you use a standard Z transformation, okay? Because it says, what is the probability that a randomly selected bag of fertilizer weighs between those two? Remember, my data points here would be the weights of my individual bags. So at this point, I am not looking at sample means. I'm not looking at taking a sample of these bags of fertilizer. I am looking at them in general as the whole population here. So my first problem is just looking at the probability that the weight of any individual bag, so we'll call it X, weighs between 14 and 16 pounds. Okay. Now, in this case, you can go ahead and plug this into your calculator under normal CDF. You have a lower bound, you have an upper bound, okay? And your mean and standard deviation are given here and here. So you could go ahead and plug in normal CDF of 14 is your lower bound, 16 is your upper bound, mean of 15, standard deviation of 1.7. I'm going to go ahead and do the long way like I did in class with the Z transformation, just to make sure we're all on the same page and you can see the difference between this and the other one, okay? But what you could do with a Z transformation is do the data point minus the mean divided by the standard deviation. And same on the other side. Okay. Now, once you have done this Z transformation, okay, let's do a quick calculation here. That would be, you end up with the probability that you have negative 0.5882. Now, X minus the mean divided by the standard deviation is just Z. And this one here is that, okay? So that is what you end up with. Now what you have done by doing this Z transformation, you now have a lower bound, an upper bound, but by doing the Z transformation, remember you've pulled the mean back to 0 and you've now got a standard deviation of 1. So what I could now type in is my lower bound, my upper bound, and then a mean of 0 and a standard deviation of 1. Okay, so two ways of doing it. Either you, in this case, because you have a strict lower and upper bound, you're not just dealing with a less than or a greater than here. Because you actually have two bounds that are given, you could just type in lower bound of 14, upper bound of 16, mean of 15, standard deviation of 1.7. Or you could go ahead and do this Z transformation to get it down to this with a mean of 0 and standard deviation of 1. Okay. And I think you actually end up with, if you type that into your calculator under normal CDF, you should end up with 0.4436. Okay. Now, the second part of the problem is the new part that we haven't looked at yet. So it says if 35 bags are randomly selected, so I've taken a sample of 35 of these bags of fertilizer, find the probability that the average weight of 35 bags will be between 14 and 16 pounds. So I am now looking at what is the probability that the mean of my sample lies between 14 and 16. Not an individual bag, but the mean of the sample of these 35 bags lies between 14 and 16. So I'm looking at what is the probability that my sample mean lands between 14 and 16 when I've taken a sample of 35 bags. So I'm going to use my Z transformation here. Okay, I've got to use my Z transformation to figure out my lower and upper bound. You can't just plug some stuff in here. You actually have to do some calculation before you plug it into your calculator. So you've got to do a Z transformation. So remember, our Z transformation in this case is the sample mean minus the population mean over standard deviation over the square root of the sample size. So this becomes 14 minus my population mean was 15 over the standard deviation divided by the square root of the sample size. Same thing in the middle. Whatever you do to one side, you do to the other. So make sure you do this all the way along. Okay. So you can go ahead and figure this out, and you end up with the probability that Z lands between 3.48 and negative 3.48. What you should find whenever you do one of these, okay, in this case, they've taken 2 points that land one either side of that population mean. So they're looking at a sample mean that is between 14 and 16, and the population mean lies right in the middle. So you should actually end up with a positive and negative of the same number here. Doesn't always happen, but it happens a lot of the time. So we want the probability that Z lies between negative 3.48 and 3.48, okay? What we have done here is a Z transformation. So I have now brought it back to a mean of 0 and a standard deviation of 1, okay? So make sure you do this Z transformation, and make sure that you always do it this way whenever you are looking at sample means, okay? So we are doing a Z transformation for the sample means here, okay? So I can now go ahead and plug into my calculator, normal CDF. My lower bound is negative 3.48, upper bound is 3.48, mean of 0, standard deviation of 1. And you should come out with 0.9995. Okay, that makes sense because you're just over 3 standard deviations or so either side of the mean here. So this makes sense because remember, within 3 standard deviations, we have roughly 99.7% of the data. So that's 9.997. So this makes sense with the numbers that we have. Okay. Okay, now I want to look at this example. This comes from the homework. This one is very similar to what we have just done. It's just more of an open-ended one, and then the following one will be the one that's kind of different to this. What this says is Thompson & Thompson is a steel bolts manufacturing company. Their steel bolts have a mean diameter of 142 millimeters and a standard deviation of 6 millimeters. Again, they've actually taken the same sample size here as what I had. If a random sample of 35 steel bolts is selected, what is the probability that the sample mean will be greater than 139.7 millimeters? Okay, so we've got a population mean of 142. Okay, so a population mean of 142. We have a standard deviation, a population standard deviation of 6. We've got a sample size of 35, and we want the probability that the sample mean is greater than 139.7. So we want the probability that the sample mean is greater than 139.7. Okay. So we've got our population mean was 142. Population standard deviation is 6, and we have a sample size of 35. So I'm going to do a Z transformation on this, okay, because we've got a very open-ended thing here, okay. We've got a lower bound, but we've got no upper bound. Now, usually when we've done a Z transformation, we can then use our upper bound of 10. You couldn't use an upper bound of 10 here, it would make no sense. So let's do a Z transformation here. And it would give me the probability of x bar minus the mean over the standard deviation over the square root of the sample size is greater than minus the mean divided by 6 over the square root of 35. Okay, if we quickly type that into a calculator, minus 142 divided by 6 divided by the square root of 35, that would give us the probability that z is greater than negative 2.27 roughly. Okay, now I am in standard normal. Okay, so now my lower bound is negative 2.27. My upper bound, I'm in standard normal. I can use an upper bound of 10. My mean is 0, standard deviation of 1. So once we've done that z transformation, I can go back to standard normal. And it's exactly what we have done before. So I've got a lower bound of negative 2.27, an upper bound of 10, mean of 0, standard deviation of 1, gives me 0.9884. Okay. So that's pretty much the same as what we did last time. It's just that you had no strict upper bound there. So we had to do some work to get it to standard normal using the z transformation for sample means. And then we can go ahead and calculate it in standard normal. Okay. Now, the other one that we have, the other example, is slightly different. And it looks like this. This time you've got a mean per capita income is $21,604 with a standard deviation of 727. What is the probability that the sample mean would differ from the true mean by more than $36 if a sample of 193 people is randomly selected? So what you want to do here, okay, is keep in mind two things. They've got differs from the mean by more than, okay? Sometimes you'll get a differs from the mean problem, which basically means that you have to look at that many dollars in this case, either side of the population mean, okay? And they want to see what is the probability that it differs by more than that. I'm going to do a quick diagram here. Let me draw this out. So remember, our sample means have a normal distribution as long as you've got a sample size of at least 30, which you do have here. Okay. It said that our population mean was 21,604. And then it has said, what is the probability that the sample mean would differ from the true mean by more than $36? So let's say you go $36 either side of 21,604. So if I did that, 36 below it is 21,568, and 36 above it would be 21,640. Okay. So if I've gone $36 either side of that mean, they want the probability that it differs by more than $36. So they want the probability that you land either over here or over here. Okay, if they wanted what is the probability that it differs by less than $36, you'd be looking at the area here. Okay, but it's what is the probability that it differs by more than $36. So in this case, what I'm going to do is I'm actually going to figure out the probability that it differs by less than $36. Okay, and I'm going to look at the area here. Then if I do 1 minus that probability, I'll get the probability that it differs by more than $36. Okay, so first of all, what I'm going to do is find the probability that the sample mean actually lands between these two values so that it differs by at most $36 from what that population mean was. Okay, I'm going to do my z transformation here. So I've got the probability of 21,568 minus the mean divided by the standard deviation of 727 over the square root of the sample size, which is 193. I'm going to run out of space here, so I'll do this down here. So I'm going to get 21,640 minus the mean divided by the standard deviation over the sample size. Okay. So once we figure all of that out, let's plug this into a calculator quickly. I should get 36 divided by 727 divided by the square root of 193. So I should get the probability of z being between, I'm actually going to put that at 0.69, I'm going to round it, is less than or equal to z, which is less than or equal to 0.69. Okay, so I'm looking at the probability, okay, I've figured out both of these values here and here on a calculator. I'm looking at the probability that z lands between negative 0.69 and positive 0.69. Again, I am in standard normal at this point. I've done a z transformation, so my mean is 0, my standard deviation is 1. So if I plug this into a calculator, okay, let's go to normal CDF, my lower bound is negative 0.69, my upper bound is 0.69, mean of 0, standard deviation of 1. So that should give you, if you type it into a calculator, 0.5098. But what we have done, as I said, is we have figured out what is the probability that you land in this area here, so that the sample mean will differ from this population mean by less than 36, okay? But we want, what is the probability that it differs by more than 36, which is these areas out here. So what I need to do is 1 minus this answer. So if I do 1 minus 0.5098, do 1 minus that answer, I end up with 0.4902. Okay, so this is the probability that my sample mean will have a difference of greater than 36 compared to my population mean. So it's going to be at least 36 away from my population mean. Okay, so whenever you see a differs by problem, you have to look at both sides. So you have to add and subtract, in this case 36, from your population mean. Okay, if it differs by less than that value, you look at this inside piece here. When it differs by more than that value, you'll have to do 1 minus that to figure out what is the probability that you land out here. Okay, that is all of the central limit theorem. Most of those problems are pretty much exactly like what we have just done. They are either one of these problems where you have what is the probability that the sample mean just is greater than or less than or between two values, or it will be what is the probability that they differ from the population mean by a certain amount.